Okay, let's begin. We're going to continue with our little segue here. Last time, we defined what we called an antiderivative. So we said big F of x is an antiderivative of little f of x. If you take the derivative of big F of x, you get little f of x. We also spoke about the fact that the big F is not a unique function. It is possible for your function to not have any antiderivative. It is also possible for your function to have an infinite number of antiderivatives, because if this guy includes any constant term, then that will be eliminated once you differentiate, and so this wasn't unique. This led us to not only the notation for this, but also the fact that the idea of a general antiderivative, when we spoke about the fact that we might denote it this way, where plus is called an arbitrary constant, and so this is just called the antiderivative of f, or another word we might call it is the integral of f. And in fact, and this is something that will be made clear a little bit later, we might emphasize this one by calling it the indefinite integral. It's indefinite because the plus c could be anything, it's arbitrary, we don't know for sure exactly what it is unless we're given more information, like we were, for example, in the word problem that we did. So it's called the indefinite integral. We know that this is the general antiderivative, but we don't know specifically what it is. We're not definitely sure what exactly it is, but we do know it would have this form. And then we made some remarks here, which is where we kind of ended. So the first remark was that antiderivative rules could be obtained by reversing derivative rules. So that follows almost immediately by the definition of antiderivative. Second thing, of course, it wasn't just a party trick, it was antiderivatives were useful. We used it to solve a problem that we knew, it felt to us like it could be solved because there was, derivatives were obviously involved here, but by just knowing about derivatives, we actually couldn't solve the problem. And we ended there. So now comes the third remark. And this remark is kind of surprising, and this is really where the segue to the second part of our course happens. And it is the fact that antiderivatives have a special connection to area. And that might seem surprising. It was surprising to a lot of people when they first started noticing it. And so let me illustrate what I'm talking about. Suppose you have a function on an interval, say it starts at a, but I let the right interval vary, right? So I know it starts at a, but I can vary where the endpoint is, so I just call it x. So it's doing its thing. So our function over here is x, that's y. It's doing whatever it wants to do, that's f of x. And I can pick a point A as the starting point, and I can increase this to some random point called x. Right? So of course that's going to be the output value is of course going to be f of x here. And of course I can move this at will. So the x values can change, and I can pick even some other x value if I wanted to, and let's be very suggestive here and say this other x value I pick can be a distance of h away. So I can even think about two possibilities under this function. Now here's where things get interesting. Suppose you could find a function which I'm going to call big A of x, that gives the area under f on ax. So I'm not going to say such a function exists, I'm not even going to tell you how to compute it at the moment, but let's pretend that we could actually do that. Let's suppose there was a way, a formulaic way to measure the area under this curve. Right? And the area is going to be given by A of x. Right? So A could be anything, so it could be 1, and then if x is 2, this will find the area under the curve between 1 and 2. If x is 3, plug in 3 to this function, it'll give you the area under the curve between 1 and 3, etc. So I have a function that can measure the area up to x. And of course, this formula can be extended so area, so this formula has the domain going all the way from here to x, but of course I can kind of extend that formula and talk about the area all the way up to the point x plus h, and I'll get a little bit more area under here. But that's kind of the picture. Suppose we could find a function that would actually do this. What would that function have to behave like? Well, I'm going to show you what this function would have to behave like. We're going to do an argument here, which would require me to actually tweak this picture a little bit. So let's actually throw in some constructions here. This is a rectangle. Think of that as just a rectangle sitting on top of the x-axis. Notice that its height is given by f of x. So I can call that, that's a rectangle, call it R1. I can create a second rectangle. The rectangle is going to be this guy. That just touches the little extra piece, it covers the extra piece of area that this first rectangle missed. That's just on top of that. We call that rectangle 2. And this little piece of the area that the A of x function would have gotten, that's not in R1, but it's in R2. I will call that, don't have a lot of letters for that, let's just call that the excess. That's the excess amount of area that R1 didn't capture, that extra little bit of area. So now let's talk about the following idea. Let's say one thing you could realize is that the blue area, if I really only cared about the blue area, one way I could find the blue area is to take the entire area up to here and subtract the entire area from there. Right? Maybe I'm interested in this extra little piece that I get by extending the x a little bit. And so here you realize that, here you realize that if I were to take the area function evaluated at x plus h and subtract the area function evaluated at x, that is going to give me the blue area. It's going to give me this guy. Okay, so now let's talk about the blue area. How is the blue area composed? Well, that's the area of R1 added to the area of the excess. That's how I would get that blue area. take the area under this rectangle and then add in that little piece that I missed. That's the excess. Now note the following. Here are some things that would actually happen. If I look at the area of R2 and divide it by H, what would that become? Well, let's give that a name, shall we? Let's say the height of this is some number n. So some number n, it doesn't matter, just picking around it. So the area of R2 would be, of course, its width is h, and its height is n. So this would, of course, be n times h. Of course, those would cancel. You would get n is what this ratio would be. And now if you kind of consider what would n look like if this guy was getting smaller, right? Well, that would mean this point would be getting closer to that point. The height of this rectangle would be getting smaller. And so you can basically know that this guy will approach 0 as h gets close to 0, as we close in the endpoints together. Of course, this implies that the excess over h will do the same thing. Because it's just a part of that rectangle. If the area of the entire rectangle is going to 0, then surely this piece of it will, its area will also go to 0. Okay. What is the point of that? Well, basically what I just said was, we now know that if this guy is actually equal to the area of R1. Now the area of R1, if we take height times width, the height is f of x, the width is h. So this is going to be f of x times h plus the little bit of excess. What I'm going to do now is divide both sides by h. See that the left side is starting to look like a difference quotient. It's burned in our brains at this point. We're probably getting nightmares about difference quotients now. And so we might think, oh, what would happen if we take the limit of that difference quotient as the denominator approaches 0? Well, we know what would happen. That will give us the derivative of the area function. But that's going to be the limit as h approaches 0 of f of x plus this excess over h. Now, limit as h approaches 0 of f of x is, well, it's just f of x. There's no h's in that. And we just explained that this guy is going to approach 0 as h approaches 0, so that part is going to go off to 0. And so we end up with this relationship here. And of course, what does that mean? What would you be able to say here? That means that a of x is the antiderivative of f. On this integral. Which is a strange thing to actually show up. Somehow that reversing a derivative is connected to an area in this particular way. And so we might say, would something like that always happen? Well, we know about one situation in which it would be true, and it's the situation that we've actually looked at before to talk about derivatives. So let's examine that example again. A long time ago, also, we saw this example a while back. This was when we were first trying to figure out the solution to the rate problem. This was an x and y. We had a thought experiment. We're tracking the position of an object over time in hours, and we're tracking its distance in miles. And we saw that, okay, after 3 hours it covered 150 miles, and we were assuming that it traveled at a constant speed. And so what we realized here was the slope gave us the velocity of this object. Right? That was a really cool thing to figure out, and we actually used that idea to develop the derivative. So the derivative fell out of this. Now, what would have happened had we continued? Well, we know that we can think of the derivative as a function, and now we know that when we take its derivatives, we can think of those guys as functions a lot of the times. And so if we kept along with this function idea, and we could realize, okay, the slope we can think of as a function, and what would its graph look like? Well, in this situation, if I was plotting the velocity, well, in this case, the velocity is the slope. You have a constant slope here of 50, right, rise over run. So this would just be a horizontal function, 50. And if I consider that function over the same time period, you'll notice something quite curious happens. If we were to take the area under that function, it would be 150, which happens to be the distance that the object covered. And it turns out that people would be doing this all the time, and they'll always be getting the same answer. Obviously, there's something going on here. Right? And you can do this. You can plot a function, and you can plot its derivative, and you'll realize the area under the derivative is always going to be outputting the y values of the original function. And so here, it seems that it also works in the distance and velocity case. Here, it would seem that if you find the area under the velocity function on the interval AB, it actually gave us the change in position. Our change in position was 150, and the area under the velocity function in that same time period is 150. Or, more generally, you could realize that the area under f, right? F is representing some function on some interval, is equal to its antiderivative evaluated at the endpoints of that interval. And the answer is yes, this is true in general. As long as this antiderivative can exist, and of course our function has to behave nicely in a certain way, it turns out that that's actually true. And that is the beginning, that thought is the beginning of calculus class. This thought is what led to the fundamental theorem of calculus. And again, it kind of popped out of nowhere. One, it was kind of difficult for us to actually notice what was going on for a long time because graphs didn't exist for a long time. You might have remembered, well, I don't think I mentioned to you guys, but the XY plane, a couple people have been attributed to come up with this. Fermat is the most famous one, and this was around the 1600s, right? So there was no Cartesian plane before that point. So the idea of picturing an equation or thinking of the picture of a formula wasn't really a thing. Analytical geometry didn't really exist. And so the kind of things that would jump out to you from looking at pictures wasn't really a thing that we had the privilege of being able to do. But since we started having pictures, certain things would become more obvious, and then we'd start to see these connections that it wouldn't be obvious just looking at a bunch of equations on a page. And so that was a part of the reason. And then, of course, people started studying things like this. Isaac Newton, for example, was studying the motions of the planets in our solar system. And of course, he wanted to talk about their speed. And he started graphing their speed. And he kind of noticed this relationship. And, well, he and his math professor noticed this relationship. He was probably the first guy who came up with this idea, Isaac Newton's teacher. But ultimately they came up with this idea and they're like, so you're telling me there's a connection between derivative and area? And that's where it came up. Because we've been talking about finding rates of change, and that was a set of mathematics over here. And then a bunch of people were figuring out how to find areas, and that was a set of mathematics over here. And they realized, oh, the derivative helps us find rate of change, and now it's like, there's like a beeline, there's a connection from over here to over there. Quite interesting. So it turns out that that is true in general, and you might wonder, why is that true in general? And the main answer is the mean value theorem. And you might say, what the heck are you talking about, Javon? Because I know the mean value theorem, it doesn't say anything about area. That's what you think. We're going to see that it does tell us about area. But this was a very important thing. But just seeing a few examples of it happening wasn't good enough. It's not good enough for math people. We needed to know how to prove that it would always work in general, no matter which two functions I pick. If I can find a function that's continuous on an interval, and I can find its antiderivative, does this relationship always work out in every possible situation that anyone could come up with? That's the fundamental theorem of calculus. At least that's half of it. That's kind of why we're here today. And so now that we can see this connection, we're actually going to look at the other fundamental problem of calculus. We're going to look at the area problem. So we're going to attack the area problem right now. So way back at the beginning of the class, I told you calculus was about solving two fundamental problems. One was called the rate problem. This is figuring out how fast things move. The other one was called the area problem, figuring out how much space something takes up. These two things weren't always under the same branch of mathematics. In fact, they were studied separately for quite literally thousands of years. Archimedes knew how to find area of very odd shapes back in 300 BC. So over 2 millennia ago, we knew how to solve this problem. It's just that we didn't really know that these problems were connected until very late, close to the mid-1600s, 1700s, around there. And that's because no one had ever thought of the XY plane before that point, right? That wasn't really a thing. Picturing an equation wasn't really a thing. But once we started picturing equations, a lot of things came out of pictures. And so this allows us to attack something called the area problem. So basically what we're going to do is we're going to pretend for the moment that we don't know about derivatives or anything of that. We're pretending we're in a different part of the world at a different time. We don't know about derivatives. We're going to figure out how to find areas. And then you're going to realize that whoop, we're going to loop right back around, and we're going to end up in the derivative / antiderivative circle. And so this is figuring out how much space something takes up. Okay. Now that in and of itself is quite a vague request. What do you mean something? Oh, quite anything. It depends on the context you're talking about. We mentioned an example of the guy who has property that has a very weird shape, and you're charging him property taxes, and he wants to know that you're charging him fairly. How do you actually know how much space my land takes up? So it's basically how much space something takes up. How would you actually figure that out? As I said, we figured it out like 300 years before Christ. So it turns out that we knew about the solution to this for a very long time. The solution is simply the following. 1, dissect the object. Into a bunch of little shapes which you can find the area of. Now math people were very simple people. We always start easy. The rectangle is the easiest thing that we know how to find the area of. So if I have something that has a very irregular shape, my first thing when I want to figure out how much space that takes up is to dissect it into a bunch of rectangles. So I can slash it like this, and I can slash it like that. And because I know how to find the areas of all these rectangles, I can find the area of that irregularly shaped object by simply adding up the areas. And that's it. That's the solution to the area problem. So we have something that's very irregularly shaped. It's a very weird shape. We don't have a nice formula to find its area. So we dissect it into a bunch of stuff that we can find the area. And then we're going to add up all these guys. And of course, the finer we dissect it, the better our approximation of its area is going to be. But you can now see that obviously that's going to get quite annoying if you want to be very accurate. We have a bunch of rectangles. We don't want to spend our entire day sitting counting rectangles. That might have been the thing to do in 300 BC, but today we got stuff to do, right? So we don't want to have to actually do that. I mean, there are ways you could make this slightly more efficient. You could just use a big shape to get out the majority of the thing, and so you find that area. And then you cut around the edges to find the small, and do that. But even that, you know, we can make even a larger shape here, and do smaller shapes there. But even that can be tedious, because what happens is this gives us a method or a strategy, but it's not very formulaic. What happens is going to be dependent on the particular shape that you give me. Every problem is a very new, different problem that no one is going to have any idea what the answer is going to be. No one's going to have any remote idea of how the answer is going to behave as the shape might change, etc. Right? It was just like, give me a shape and I'll just, you know, hire someone to count the rectangles. Right? So the thing is, this is very computationally intensive and annoying. And really, only Archimedes could enjoy spending an entire day doing things like this. He quite literally spent entire days slicing up shapes to figure out their areas. And that's how he came up with the area of a circle, right? We knew that the area of a circle was pi r squared for a long time. And it's because guys like Archimedes was sitting there drawing shapes and slicing them up and counting rectangles and adding up areas. But it's not something you want to do. It's not an elegant solution to the problem. And math people love elegant solutions to things. We like to be able to say, I can do this for an infinite number of shapes, whatever you pick, whatever you can come up with, I will know the answer to it. That's a part of a mathematician's pride. So it doesn't depend, we want to get away from depending on the exact example and very crude, computationally intensive methods. So it became necessary to get good at adding stuff up. How are you going to find a sum of a bunch of things in the most efficient way possible? Now, that leads to a topic in math called series, where we consider things that are called series. And this led to series and sigma notation. Now, sigma is just a letter in the Greek alphabet, the uppercase letter, the symbol is that. Sigma is like the Greek letter S, it stands for sum. So again, even back then mathematicians weren't really good at naming stuff. What do we call it? S for sum? Okay, so that's what they decided to call it. And the Greeks had the first crack at this problem, and so they chose the symbol that they wanted to use. And so it's called sigma notation. And so now we're going to jump to Appendix E in your textbook. So this is an actual topic in the section, it's in the appendix, I believe it's E. It wasn't B in the previous version, the previous edition, but it's Appendix E. And this is talking about sigma notation. And this is basically now we're going to learn how to add stuff up. And so, let A1, A2, A3, AN be real numbers. Let's say I have a list of real numbers and I want to add them up. First of all, we have to look cool while we're doing it, so we're going to come up with a nice little notation for saying we're adding stuff up. We define the following: sigma of the AI. So here I'm using I to track the subscripts. You can think of this as just a list of n numbers, right? Where I'm just calling them by using a variable to call them by a different name. So A1 is the first number in the list, A2 is the second number, A3 is the third number, and so on and so forth. And so I can use I to track the position in the list, and I can say I want to add all the ones from I goes from 1 up to n. So I can add everyone in this list. And so here, this is where we're going to start, and this tells us where we're going to end the summation. And basically, this is just a fancy way of saying, take A1, add it to A2, add it to A3, and keep doing this until you get to AN. So we can have a shorthand for adding things together, and the first step to being elegant when it comes to solving a mathematical problem is to come up with a cool notation. That's step one. You know, it's like when you want to start a business, you come up with a cool name, and then you worry about the business plan and where you're going to get the money from and all that stuff. You have to have a cool name. That has to be the start. So this is our notation. This is where it starts. We want to look fancy while we're adding stuff up. We created the sigma notation. So this is called the sigma. These things this is called the index of the sigma notation. You don't really need to know that. But it basically tells you where you want to start and end the sum. Now, when you have a list of numbers, not terribly important for you to know this at this point. This is kind of something you're going to go over in Calc 2. But a list of numbers is called a sequence. And when you add the numbers in that list, that sum is called a series. Or people will call it sum or summation. But series, math people will call it series. So we can have a list of numbers in a definite order. This is called a sequence. When you add up all these numbers, that is called a series. Okay? And so that's just a notation that we use to add a bunch of things. Now, one thing that's worth mentioning is we can extend this to infinite lists. So this gives us what we call an infinite series, as opposed to this, which is an example of a finite series. We can talk about adding up an infinite number of things. Let I start from 1 and keep going forever. And so that's just A1 plus A2 plus A3 plus forever. It just keeps going. This is called an infinite series. Now, a couple things here is once you start throwing infinity into things, things stop making sense in the conventional way. So some people might think, well, if you're adding up, well, this should only make sense if all the numbers are 0, because if you're adding up a bunch of positive numbers, it'll always just go off to infinity. It won't make sense. It's not a thing that we should care about. That would be wrong. You can add up an infinite number of positive things and not go off to infinity, or negative infinity. It is also possible to add up an infinite number of things and not get a meaningful answer at all. It's also possible to add up an infinite number of things and get infinity or negative infinity. So this is something that does require a very mathematically rigorous theoretical looking at it, because there are times when it will make sense. It will be a finite value, and we'll need to know how to add it up. And that's also something we kind of knew for a long time ago. I'm talking about a few centuries BC, that it's possible to add up an infinite number of things and get a finite answer. And I believe it was, not that guy's name, it starts with A, but he came up with paradoxes that when the guy was shooting the arrow at the target. You guys remember that? No? I'll look it up and I'll mention it next time. But there was a paradox. Basically, when he shoots the arrow at a target, and someone says, okay, if we theoretically look at this, right, you can always freeze time when the arrow is half the distance away that it used to be, right? So if it was 10 feet away, you freeze time when it was 5 feet away. Then freeze time when it was 2.5 feet away. And freeze time, right? And you go through this process in your head of saying, okay, we're always freezing it when it gets half the distance away that it used to be. And then someone would say, well, if it's always traveling at half the distance where it used to be, it'll never hit the target. But obviously in reality, it hits the target. So it has to have covered a finite number of distance, even though you can think of it as you're adding up a bunch of half distances. So you can do this dissection of time forever, and somehow you will come up with a finite answer, and that's where they kind of had the idea. This must make sense somehow. It has to give us a number somehow. So there's a way to actually do that. But that's Calc 2. Like, we're not going to really talk about that, but I'm just going to tell you that it's possible. When we get an answer here, it's going to make sense. You just have to take my word for it at this point. And in Calc 2, you're actually going to see why it would make sense. Yeah.
So, based on your example, we knew like what was the endpoint, like the distance to travel, like the arrow.
Mm-hmm.
But in these examples, it's like infinity.
Yeah. And the thing is, sometimes you would know the endpoint. So remember I said we wanted to dissect things, right?
Mm-hmm.
And of course, the more we dissect it, the better it gets. So within a finite window, we can talk about doing an infinite number of dissections. We can keep increasing the number of dissections. Every time we dissect something, you can dissect it further. So that's where the infinity is going to come into play. When we start to think of, okay, we want a better approximation. Okay, even better, even better, even better. Keep going. You'll end up having an infinite number of rectangles in theory. And so someone says, but we know it has to add up to a finite area. There has to be a number, that's the answer. So it is possible to think of this as a finite number in certain contexts. Okay. But so far we don't know any of that. We're just looking at a cool notation, a cool way to write this down and look fancy. Okay. At this point, maybe I should give you an example. Because also at this point we don't have much time left. So yeah, let me give you a quick example, and then I'll give you a formula that you should know. There are about 4 formulas that you should know like this. I'm going to talk about one of them today. Let's do an example first. What I want you to also know is that we can think of AI can be thought of as a formula. Whose outputs gives the values in a sequence. So more specifically, it could be thought of as a function, and that's how function theory comes into this, and whose inputs are from the natural numbers, 1, 2, 3. So we can map, plug in 1 as the input, A1 is the output. Plug in 2 as the input, A2 is the output, and so on and so forth. And so we can introduce functions into talking about these sort of things. But let's get into an example here. Suppose I give you this formula. So the AI is this, and I say I want you to find the sum. I goes from 1 up to 3 of this formula. So that basically means you want to start at I value 1. You're going to plug it into this formula. 1 plus 2. And that's when I equals 1. Plus, you're going to plug I equals 2 into that formula. 2 plus 2. That's for I equals 2. Plus, plug in 3 into this formula. That'll give you 3 plus 2. And that's for I equals 1, I equals 2, I equals 3. And so this would be 3 plus 4 plus 5. And that would be 7 plus 5, that would be 12. So I can do that. And I want you to know we don't always have to start at the beginning. We can start anywhere we want. So I could have started at, I don't know, 2. And go to 4. And so of AI, that would be A2 plus A3 plus A4. And that would be 2 plus 2 by plugging into the formula, 3 plus 2 by plugging into the formula, 4 plus 2 by plugging into the formula. That would be 4 plus 5 plus 6, and that would be 15. So now you might say, sure, we look cool, but you didn't really save us from doing a bunch of computation here. When is it going to get easier? Well, the thing is we can come up with formulas, and then using function theory and these formulas, we can manipulate things to add things up very efficiently. So consider this one. This is the first of like 4 formulas we're going to want to be able to do. And this one shouldn't be too bad. Legend has it, the mathematician Carl Friedrich Gauss figured this out when he was like 4 or 5 years old. So we should not have any trouble with it. So this is saying we're just adding up I, right? So I equals 1, then 2, then 3. Right? So this is just a fancy way of adding up the first n positive integers. Now, there's a legendary story here. I don't know if it's true, but I actually would not be surprised to know that it was true. Of when little Gauss was like 4 or 5 years old, he was in preschool, and he and his class were kicking up a ruckus, and the teacher got really upset at them, and they were just learning how to add things by literally with physical shape. Okay, 2 marbles plus 3 marbles is 5. Of course, Gauss had been doing arithmetic at home in his spare time for a while now, and so when the teacher decided to quiet down the class and say, everyone be quiet, add all the numbers from 1 to 1,000, she thought she would have them busy and preoccupied for the entire evening, if not the entire semester. However, Gauss gave her the answer within a couple minutes. So he thought the following. Okay, so let S be this thing that she wants us to get. And she actually wants us to get 1 plus 2 plus 3 plus all the way up to 1,000. And he's looking around at all his friends trying to count on their fingers and trying to figure out the answer. Whereas he noticed something special. Well, he knew about the fact that arithmetic was addition is commutative, which means the order shouldn't matter. So he turned it backwards. And then he noticed something curious. If you add these guys up in this order, you'll notice that you're always getting the same number. You notice that this is 1,001. And that's also 1,001. And so on and so forth. So this is just adding up a bunch of 1,001s. How many 1,001s? Well, 1,000 of them. Right? So he added the list twice, so of course he didn't have S here, he had 2S. And so he figured out that 2S is going to be 1,000 times 1,001, and then divide both sides by 2, and that's going to be the answer. So while everyone was there trying to count on their fingers, he computed this number and gave it to his teacher. And it turns out that this works out in general. So I can imagine this going up to n, and I can write from n minus 1 all the way backwards. We can add it all up. You'll always realize that this will be n plus 1, n plus 1, n plus 1. There will be n such terms, and because you added it twice, you divided by 2 to get a nicer answer. And so it turns out, we actually know quite well that if we add up the first n positive integers, the result is always going to be n times n plus 1 all over 2. That was the first formula. Now we're getting quite efficient. We're not going to sit around adding up 1 to 1,000, we're just going to plug things into this formula, which we can now concisely express that idea in sigma notation. We'll continue next time. We'll get even better at adding things up. And then we're going to actually try to solve the area problem.
So wait, that's much?